Hello and welcome to this free preview lecture series of my on-demand FE Electrical and Computer Exam Preparation course. In this lecture, we are going to tackle arguably the most difficult concept within probability and statistics from the standpoint of FE Electrical and Computer Exam Preparation, and this topic is Bayes Theorem. But before we dive into the content, I would really appreciate if you could like this video, click the subscribe button and the bell icon if you haven't already done so. Hello and welcome to this lecture on the topic of Bayes Theorem, which is a subsection of probability and statistics. So in this lecture, we are going to take a deep dive into Bayes Theorem. We will start with an overview of Bayes Theorem, then we will do a derivation. The reason I'm doing derivation of Bayes Theorem is to help you see how the theorem is constructed. We will use the law of joint total probability and conditional probabilities in order to derive Bayes Theorem. And finally, we will take a look at the mathematical equation. As I pointed out in the introductory lecture, Bayes theorem happens to be one of the most confusing topics within probability and statistics as far as FE electrical and computer exam preparation is concerned. So hopefully, after going through multiple examples that are discussed in this lecture and looking at the derivation and mathematical equation, you will be able to tackle this type of problem on exam much more easily. So what is Bayes theorem? Bayes theorem actually allows us to calculate conditional probability of B given A, when the other conditional probability is known. And it is based on laws of total probability and conditional probabilities, which we will use in the derivation. So why are we ever concerned or interested in finding P of B given A when P of A given B is provided to us? Well, there are a lot of probabilities which are easy to calculate in one direction only, okay? And that's why if you're given this type of a conditional probability, then calculating this type of conditional probability is sometimes desired, right? And Bayes theorem allows us to do that. So we've already looked at law of probability number 3, which was the law of compound or joint probability, according to which the probability of A and B happening was equal to probability of A times probability of B given A, or probability of B times probability of A given B. That was discussed in the last lecture. Now what I'm going to do is I will set these two equations equal to each other, okay? And this is the result. And we basically divide the entire equation by probability of A. So this equation that we arrive at, which basically tells us that the probability of B given A is equal to probability of B times probability of A given B divided by probability of A. If you look at it, then we are basically being able to calculate one conditional probability in terms of the other conditional probability. And this comes in handy when it is easier to calculate this type of a probability, okay? And it's not easy to calculate the probability other way around. When you look at the NCS FE reference handbook, the formula looks slightly different. Okay, this is a much more simpler formula, but in NCS FE reference handbook, they have this summation term happening in the denominator. So I'll explain what that means. So in order to explain the formula that's provided in NCS FE reference handbook, we have to revisit law of total probability. Now the law of total probability, when we reviewed, we expressed it in this form where probability of A union B was equal to probability of A plus probability of B minus probability of A intersection B. Okay. Now there's another variation of probability, law of total probability, which we can explain in the form of Venn diagram. So let's say you have a sample space S, which is comprised of B1 and B2. Now you can see that this sample space S is equal to B1 plus B2, and B1 and B2 are both mutually exclusive. There's no overlap. Now, law of total probability tells us that if you have A, okay, any set A, then this A will basically be equal to the intersection of, will be equal to the sum of intersection of A with B1 and A with B2. Okay, and you can see that the intersection of A with B1 results in this portion, and A with B2 results in this portion. Okay, so probability of A is equal to probability sum of probability of A intersection B1 and A intersection B2. Now A intersection B1, which is based on the law of compound or joint probability, we have this. Okay, so if you replace this with A comma B1, then we basically get probability of B1 times probability of A given B1. Okay, so probability of A intersection B1 is equal to probability of B1 times probability of A given B1. Similarly, probability of A intersection B2 is equal to probability of B2 times probability of A given B2. Okay, that comes from here. Now, what you have to do is you will simply substitute probability of A intersection B1 over here and probability of A intersection B2 over here. And this will result in probability of A being equal to probability of B1 times probability of A given B1 plus probability of B2 times probability of A given B2. Now, if I were to divide this sample space not just into B1 and B2, but into many mutually exclusive portions, okay, up to Bn, then the general form of this equation would be this summation in the denominator, right? So I have probability of A, which is appearing in both cases. Okay, so I have probability of A over here, so that remains same, given probability given Bi. Okay, so in this case we had two values of I, just 1 and 2. You can have up to n values of I, so you're just going to sum times the probability of, you're just going to increment times the probability of Bi. Okay, and when you expand it, if I were to expand it, this can take the form of probability of A given B1 times probability of B1 plus probability of A given B2 times probability of B2. And this is where we stopped, right? For this given scenario, this is it. But if this went up to n, this would be plus 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 probability of A given Bn and times the probability of Bn. Okay, and that is all covered in this summation. So this is how NCS FE Reference Handbook presents Bayes theorem. And the more simpler form of Bayes theorem, if you are dealing with just probability of A and probability of B, is just this equation here. So your probability of A, we started from here. So your probability of A, I explained by using law of total probability and conditional probability that it is equal to this summation that appears in the denominator. Let us now work through a couple of practice problems, and they will help you better understand Bayes theorem and how these conditional probabilities come into play. Okay, so if you want, you can pause this video, pause this lecture right now, and read this statement on your own, because these word problems when it comes to Bayes theorem have details which you probably would have to read a couple of times. Okay, so we have a study which tells us that 1% of all people will develop a certain chronic disease, and Bayes theorem finds application in testing and diagnostics. A lot of examples you'll come across will be of this type. Okay, so 1% of all the people will basically develop this chronic disease, whatever it is, some point in their lives. So 90% of the tests that are done for this chronic disease are accurate. Okay, they are true positives. So if the test is telling you that you have a disease, then you have a disease, and that is 90% of the cases. Whereas 10% of the test will result in false positive. So 1 out of 10 tests will basically tell you that you have a disease when you actually don't have a disease. So what is the probability of someone having this chronic disease given that their test is positive? Okay, so this final statement, you have to read it very carefully. because I'll tell you what happens. A lot of students will say that, is this 90% not already given to us? Is this probability not already given to us? Well, this particular probability, which you will guess as this one, is basically telling you that 90% of these tests correctly detect. Okay, so the person has disease and the test is also positive. But what we are asking for is that we are guaranteed that that somebody has disease given that the test is positive. Okay, this is the other way around. This is that you have the disease, okay, and the test is positive. So you already know that the person has the disease, okay, and the test is positive. So it is an accurate test. But what we are asking for here is that if you're given that the test is positive, what is the probability that the person actually has the disease? So these are two different things. So for these type of problems, I always recommend to make a list of the probabilities that are given to you and clearly define them. Okay, so probability of getting the disease for the general population is 1%, so 0.01. Probability of not having the disease is probability of d prime, so which is 1 minus probability of d. Okay, so 1 minus 0.01 is 99% or 0.99. Probability of a positive test result given that the person has disease. Okay, so given that the person already has the disease and you're getting a true positive is 90%. So the test is accurate. Okay, so this is very important piece of the puzzle. It's very important to understand this part. And probability of a positive result given that person doesn't have a disease is probability of getting the positive result given d prime. Okay, so this is a false positive and this is 10%. So what we are being asked to calculate is the probability of having the disease given that you have a positive result. Okay, now whether it is true positive or false positive, you don't know, right? So what is the probability that it will be a true positive? Okay, what is the probability that it will be a true positive that you actually have the disease given that the test is positive? Now, if you look at all of these probabilities that you have calculated or identified as unknown, you find that you are given this probability of positive given that the person has disease, and you're being asked to calculate the other conditional probability, that is the person actually has a disease given that the test was positive. So probability of a true positive. Okay, so probability of D given a positive result is equal to probability of D times probability of a positive given D and divided by this, which is basically an expansion of the summation formula that we saw earlier. Okay, so the good thing about that summation formula, which I explained to you before, is that once you have listed out all of these probabilities, you can just substitute it. Okay, understanding that formula is a little bit difficult, but it comes in handy and it will basically cover all possible scenarios. And you simply substitute these probabilities that you have figured out, and you'll find that the answer is 8.33%. Again, you can see why students become confused because of the attempt to, I guess, directly jump at conclusion without really recognizing it as, first of all, a Bayes theorem, that you're dealing with two different conditional probabilities. That's one thing. And sometimes they skip this step. Okay, if you skip this step, then once you start getting into substituting these probabilities, right? I mean, if you have not clearly laid these probabilities out, chances are that you might mix these numbers up. And if you mix these numbers up, then there's no way that you're getting the right answer. Let's look at a problem from study guide. And in this problem, we are being told that according to data collected by a superstore chain, 20% of the customers prefer online shopping, whereas remaining customers prefer in-store shopping. And 50% of the customers preferring online shopping are under 30 years of age, and 40% of customers preferring in-store shopping are under 30 years of age. Okay, so what is the probability of a randomly selected customer having preference for online shopping given that the person is under the age of 30? So if you want to stop the lecture right now and read through it a couple of times, please go ahead. Basically what's going on over here is that you have been given conditional probabilities, right? You have been given one conditional probability, in fact 2 conditional probabilities over here, and you're being asked to find other conditional probabilities. So most definitely this is a Bayes theorem problem, and as I explained to you, if before even thinking too hard about the problem, you should clearly list out all the probabilities that are given to you and the probabilities that you need to calculate, because once you do that, that is more than half of the solution already. So in order to clearly lay out these probabilities, let us define X as the online customers and Y as the in-store customers. So probability of a customer preferring online shopping is already provided to us as 20%, right? So 20% of the customers prefer online shopping. So it automatically means that remaining customers prefer in-store shopping, which is 80%. So 1 minus 0.20. So it might be clearly given to you. Otherwise, it's pretty simple and obvious to calculate. So probability of Y is equal to 0.80. Absolute probabilities are always easy to identify in Bayes theorem. It's basically the conditional probabilities that confuses the students. So let's pay special attention to these 2 probabilities. So we are told that 50% of the customers preferring online shopping are under the age of 30, okay? And 40% of the customers preferring in-store shopping are under the age of 30. So we are told that these customers, so for example, this first group prefers online shopping, and they are under the age of 30. Okay, so we know for sure that this group prefers online shopping, okay, and then they are under the age of 30, right? So under the age of 30, given that they prefer online shopping, and under the age of 30, given that they prefer in-store shopping. So this is under the age of 30, given that they prefer in-store shopping. And what we need to calculate is customers having preference for online shopping given that they are under the age of 30. Okay, so that's the trick over here. So that's basically what confuses students, that this is online customers given that they are under the age of 30. So we can use that, this is the unknown, and we can calculate it using Bayes theorem. We have all of these probabilities already calculated. We know Px, Ps given X, Ps given X, Px, Ps given Y, and Py. So you simply substitute those probabilities and you will get this answer. So the recommendation is, first of all, to identify the problem as Bayes theorem, okay? Until unless you identify it as Bayes theorem, you won't be really able to apply the correct formula. And once you identify it, make a list of all the probabilities and think hard about the conditional probability that you have to calculate, okay? Once you set up the equation, then it's simple plug and play because you know all the probabilities and it's just simple substitution. In this lecture, we did an overview of Bayes theorem. We derived the equation and spent some time understanding some of the key parameters of that equation. Then we did some practice problems. So hopefully by going through this lecture, you have a better understanding of arguably the most difficult topic within probability and statistics from the standpoint of FE electrical and computer exam. If you found this preview lecture helpful, I am confident that you will also greatly benefit from the full course that contains over 150 lectures and covers all the topics that are found in the latest NCEES FE Electrical and Computer Exam specification. You will also get access to tons of quizzes and mini exams in this course that will help you get additional practice, along with a bonus full-length computer simulated practice exam. This streamlined and well-reviewed course comes with an amazing 30-day full refund policy, no questions asked. On top of all this, I have also included a special discount link in the text section of this video.